the Silurian, and then much more horizontal, this is the Devonian, and you can clearly see it here. You don't need to climb down at all if you are unsure about it. And I want unsure people not to climb down, but if you're dead set on climbing down, you can. We were in Loch Ness, and then we came out onto the Black Isle, and then we came back down and crossed back over, and we're basically here, and we're looking this way, and we're looking at all of this land here. And what's amazing to think though is shortly we're going to be arriving in Lairg, which is just here. We're here, it's there. It's just sort of just beyond the end of a loch. And 1 billion years ago, a meteor came and went bam into it. But then 400 million years ago, all of the rock you see in front of us was shoved all over the top of it. That's why there's no crater there. But there is a big gravity anomaly, and tomorrow when we get out into Ascent and we come here to the village of Clactol, I will take you to a place where you can find in the billion-year-old Torridonian sandstones little green glassy bits which were in it. The geologists originally interpreted this stuff as being volcanic glass, but it's been reinterpreted to be actually it's tektites. It's material from the meteor impact. So when the meteor impacted, bits of meteor and bits of the country rock went into the air, and it all rained down as liquid rock, and that's what it is. So at our next stop we're going to be right over the top of where the crater is, but there's going to be no evidence for it at all. But there's this visitor centre that's got lovely interpretation boards about it. You can buy a cup of tea, you can eat a actually one of the most calorific things you can eat is called Scottish tablet. It's basically just butter and sugar, and it's a kind of it's a sort of
a Scottish tablet.
It's called tablet, yeah. It's like cream, butter and sugar, and it tastes delicious, but it's very, very calorific. Stone, which is on top, the Cambrian limestone, and then this is also Cambrian, the Saltarella grit. This is also Cambrian, the Fucoid beds. This is also Cambrian, the pipe rock, and these are fossilised worm burrows. And this is also Cambrian, the basal quartzite. Unconformity, this is billion-year-old unmetamorphosed rock, and basically actually this and this is the same age, but this is metamorphosed, and up until just 5 years ago people thought, oh, this is a marine origin and that was a fluvial origin, but now the research is showing no, it's the same origin. In fact, it's not only is it the same age, it's actually the same stuff. It's just one's metamorphosed and one isn't. So yeah, these little midges. Did anyone buy any of this in the last place?
It's in them. I have to go back and get it.
I give someone a squirrel. The first thing what I'm going to point out is you see the little stack there, that little rocky island. That's stack Fada, and this tektite is in what's the stack Fada member. So you see it, and then there's a kind of band of harder rock sticking out into the sea, which almost reaches it and comes into the land. That's where we're going to walk to, and the path goes up behind that bench, and it comes sort of up and down along the coastline to get to there. It's quite tiring. It's not that bad, it's quite tiring, and the reason I'm just saying that is that's the whole reason for the walk, is to go there and to come back and to see what we saw in that centre yesterday. So if you're thinking you don't want to do it, you can just stay here. Other things I'm pointing out is on that headland there's actually the ruined remains of a broch, and a broch is an iron-aged castle. And you'll see those going to Shetland. You'll see more of those in Shetland, but it was actually built 2,000 years ago, and it would be a towered castle, and that's the remains of it. And all the molten debris.
Glass and debris.
Yeah, which is a mixture of the melted rocket hit and a mixture of the original meteorite. It goes up into the air and it rains down into the mud here, and this is what this green glass is.
Does this qualify?
And when did that all happen?
1.2 billion years ago.
Wow.
And they saw shock in the glass that they
They've
know.
seen that in the glass. They found iridium. They've also found, which is very rare mineral on this earth, but it's more common than meteorites. They also found zircon crystals, and within the zircon crystals there are little veins of, I forget the name of the mineral, but it's a shock mineral. It only forms under extremely high pressures.
Stishovite?
It's not actually stishovite. The stishovite is a well-known mineral that when we actually go on our Germany trip, there's a church thing here on Torridonian sandstone. If we can examine it here, you see all this is layers of Torridonian sandstone. But then the headland over there, it's Lewisian, but there's a whole load of conglomerate there, which is Torridonian. That's a paleo surface. It's a whole scree, sort of debris slope of Torridonian. Can you see there, which is on the Lewisian. But then here, not quite as big as the hotel, but this lump here, this is the boulder. But it's at least the size of that house. This is the boulder, and this is made from Lewisian gneiss. But when you actually come down to the beach, which we will, and you examine closely, you will see that there are veins of mudstone that come right up through it everywhere. And we'll go and examine it, and it's hard to see from here. It's easy to see when it's wet actually, but you will notice that all these veins of mudstone, and what the interpretation is that this whole chunk actually fell down this paleo canyon, and you can see part of the canyon walls here. Here's the scree slope on it, but it fell from higher up this canyon 1.2 billion years ago, smacked into the mud at the bottom, and the cracks injected this through. And as I say, there's a National Geographic article all about this, published about 3 years ago, which I've got a link to in the handout. So you should look that up.
Oh yeah.
And the boulder on the other side of that cleft as well? Is it just cut?
No, I think the boulder is just this piece here. This piece here, but the fence goes up over the top of the boulder, so the boulder goes inland a bit. Yeah. And as I said to you in the coach, the amazing story of the students who are here, and they always came here, and it's marked on the geological map as a fault here, and actually that surface is quite a flat surface, so maybe there is a fault through here as well, after all this boulder had fallen and some hundreds of millions of years after. But it was just marked as a faulted contact, but then there's a whole load of the Torridonian not faulted. That's just an unconformity. That's just a conglomerate, billion-year-old conglomerate sitting on top of Lewisian.
Yes.
And it's as if it slipped down yesterday, but it slipped down 1 billion years ago, which is amazing, isn't it? So what we'll do is we'll go down onto the beach, and let's go and have a look at some of these sort of mud dikes coming through the boulder. So here we are looking at the classic unconformity here on the shores of Loch Assynt. And at the base here you've got the 3 billion year old Lewisian gneiss, some of the oldest rocks anywhere on the planet, and you have a 2 billion year time gap here. That's half of Earth history just missing, and on top of it is completely unmetamorphosed 1 billion year old Torridonian sandstones. And these sandstones formed from the erosion of a mountain chain that would have existed back then 1 billion years ago and had been deposited by rivers. And here we can see this cycling of the river sequences as we go up. But what an extraordinary sight. Very briefly talk just here, and then I'm going to take you down to the gorge. You can see that we can touch the rock here. You can see how it actually resembles the Torridonian sandstone quite a lot, but this is actually metamorphosed, and the Moyne supergroup goes through various stages of some of it's really quite heavily metamorphosed, and other is slightly, and this is not very heavily metamorphosed. You can still see a lot of the original sandstone bedding, but it's our chance to actually touch some of this rock from the Moyne supergroup. So that's what I'm really going to say here. Let's get down to the gorge. The answer not in the microphone. One question I was asked is about what caused this volcanism. Now, my understanding, it's all a little bit complicated. You've got a hotspot, and basically the Laurentia is moving over this hotspot, and you see the hotspot making volcanism in the west of Greenland. You see it there, and then Greenland's moving over. You can't see anything because it's under the ice. But then the hotspot gets to East Greenland, and you see volcanism in East Greenland. And basically, the North Atlantic was trying to rift open anyway. And when this rift got to the hotspot, you then had the hotspot underneath the rift, and that's what's occurring in Iceland right now. And as it's trying to move off, the rift keeps jumping. Now, when the rift sort of first got over the hotspot, somehow magma sort of spread down here much further south in the rift somehow. We're not quite sure the mechanism, and it started erupting here, even though the actual hotspot was quite a lot further north, is what I've been reading. And also somehow lava was sort of working its way under to still erupt back in West Greenland as well, even though the hotspot was between East Greenland and Iceland. So this is the sort of the latest thing that I was reading. So it wasn't so much the hotspot was actually here, the hotspot was further north, but somehow the lava was getting down through weaknesses and it was erupting here. And this is where the Atlantic broke apart. Well, it was unzipping, but this is the margin. So that's sort of my understanding of it. Do you have any better explanation to me as to why granite weathers very smoothly and rounded, whereas gabbro weathers very sharply and angularly?
Well, if you look at the mineral composition,
3 billion or 3.2 billion, nice. And then here is the amphibolite dike that works would have been basaltic. It's 2.4. In fact, it's a scory dike. But then, cutting both of them are granitic dikes. Granitic pegmatitic dikes. Here's one of it here, and it's 1,855 minutes. So you've got the 3 different generations of dikes. This is all the granitic pegmatitic dike here. This is the amphibolite. Come across now and have a look at it in detail. This has got quite a nice, see this fold here? Yeah.
Look at all the crystals.
so there's
Amphibole.
inclusions, so the dikes.
Yeah, technically, that's what I mind.
Track site, and where there's the sauropod track sites, and hopefully it takes longer to get there, and hopefully in that time it get uncovered there, and by the time we're on the way back this will be uncovered, okay? Hopefully. So this is where the tracks are, but we'll walk on for another 10 minutes or so to the next place, okay? So here we are at Staffan on the northern coast of the Isle of Skye, a globally important place for dinosaurs because it is here that mid-Jurassic dinosaur tracks and bones can be found, a time period that's missing in much of the world. And here is a wonderful stegosaur track, and you can see its 3 toes here, and at this site 2 different dinosaur trackways have been found, a stegosaur track and also a bipedal track. And just over there, just by those boulders you see to your right, a complete articulate pterosaur was actually found and recovered. But yes, a very nice track here, and you can see the barnacles highlighting the dinosaur track.
This is actually one right here.
Here we are at Loch Carusk in the stunning Black Coolins on the Isle of Skye, and all the rock all around us is made from gabbro. This rock is actually the magma chamber of an ancient volcano. Well, not that ancient, actually relatively recent in geological time, just 50-55 million years old, but this rock would have formed 30 kilometers beneath the surface of the earth, but when erosion has taken away material above it, it's risen up, and then ice age glaciation has carved out all the stunning mountains we see around us. It's carved out this beautiful valley here that's filled with this freshwater loch Carus, and there's just a little band of rock here preventing the sea from flooding in, and this being a sea loch. But when we were looking closely at the gabbro, we can see there's all sorts of inclusions within it which have been brought up from the rock below and are now entrained in the magma chamber. So here we are on the Isle of Skye in the fabulous Loch Carus, in this fabulous glaciated valley. The bedrock beneath my feet is mapped as gabbro. However, if we closely look at the gabbro, we can see that in places, well, in many places it's very, very layered and the minerals have segregated, but in other places you have much areas of much coarser crystalline material, and actually looks more quartz rich here. Perhaps this is xenoliths of basement rock, perhaps the Lewisian gneiss, which actually 3 billion years old, has been brought up into the magma chamber. If we come up here, we can see finer grained material here entrained. Perhaps this was the Torridonian sandstone. So very interesting to see. But it's all smooth, and what I'm showing you here, this is the sort of the banding of the minerals, and you've got sort of lighter, darker minerals all segregating. But the whole thing has been smoothed by the ice as well.
All right, here we are standing on some gabbro in the Isle of Skye. We are seeing an exposed magma chamber of the volcanics associated with the opening of the Atlantic. James, can you tell us a little bit more about this incredible place?
Well, yes, I mean, you've already actually said quite a lot of great things in your introduction here, but we had, for most of Scotland's geological history, it was attached to North America, and all of the rocks are part of North America until suddenly you get up to 55 million years ago and the Atlantic started to rift open, and the hot spot that's now currently under Iceland, lava somehow made its way down from there through weaknesses and erupted out in several places. Here you've got the Skye volcano, just a little bit south of us is the Rum volcano, then you've got the Ardamurchan volcano, and then you've got a volcano down on Arran. Oh, you've got the Mull volcano, and then down on Arran as well, and a huge amount of magma also erupted out in Northern Ireland. So but this exact place here, it's I believe it's probably the most beautiful place anywhere in Scotland, anywhere in the UK. And it's not just that the rocks are made from the magma chamber. These rocks actually solidified 30 kilometers below the crust. They were feeding this big volcano, and erosion has revealed them. But what is so spectacular here is the landscape. The landscape has been carved out by ice. There's been a glacier that's flowed all the way down here. Everything you're seeing is smoothed and polished. There are glacial erratics just strewn around as if the ice just left yesterday. Yeah, it's just incredibly beautiful, and we're here on a really gorgeous, lovely sunny day.
Oh, we're quite fortunate indeed. And so there's the black Cullen and the red Cullen. So how about a word or two about that?
Well, yes, there's the two different mountain ranges, the black Cullen and the red Cullen. Cullen actually just comes from the Norse word to mean mountain, because actually Vikings came here. But the black Cullen are called the black Cullen because they're black in colour. The red Cullen are red in colour. Why would this be? Well, the black Cullen are predominantly made from gabbro, although there's some other ultramafic rocks like peridiotites here as well, whereas the red Cullen are made from granites, and these both would have been formed in the same volcano, but maybe at slightly different times, and granite can form when you have a fractional crystallization within a magma chamber, and over time compositions can become more quartz rich and granitic melts can form.
So quite a dramatic place on a beautiful day. James, thank you so much for showing us around.
For GeoWorld Travel.
A couple of things out here. This is Jurassic aged. You've got a whole sequence of Jurassic stratigraphy going down the shores of this loch. It's all a little older than where the dinosaur remains are, until you get right to the far back of the loch, and then it gets to the age of the dinosaur beds, and some dinosaur bones have actually been found. But this is kind of, you know, ranging from the early Jurassic to the mid-Jurassic. So this is kind of, you know, the later part of the early Jurassic, and the stratigraphy goes down and it properly gets to the dinosaur bed. So this is a different age to what was either in Broadford or dinosaurs. It's sort of in between. But you can see you've got this sort of pale colour to it. You can see that there is a dike running up here, and it meets, and two dikes come up together and they meet. And then in this cliff where this lady sat, and we're going to go and have a look there, you can see this honeycomb weathering. And my interpretation of it is sea spray gets blown onto the cliff, and then when salt crystallizes out, it flecks off the sand grains and it makes the honeycomb weathering. So that's what we're going to look at. And then we'll come around the corner from there and walk down the stratigraphy. I'm not sure how far we'll go, but for a way I've never been very far down. I haven't had this much time here before, but there are various dikes, and at some point you start to find fossils in the Jurassic material, and if anyone can find them, Steve is probably our man. So we'll come and have a look at the honeycomb. And also the boat race starts at 3 o'clock, so we should get views of the boat race while we're looking at the geology. Here we are at the iconic Bingall's Cave on the Isle of Stafford in Scotland. Arguably, this could be one of the best examples of columnar cooling anywhere in the world. You see behind us these wonderful hexagonal columns. Well, these are formed from when lava has had time to cool, is either in a sill or a thick lava flow, and all of this lava has been produced by the Mole volcano, and it's all due to the splitting of the Atlantic. And there's a little fault that sea has exploited, and it's carved into the cave. Now, legend has it that these basalt columns that I'm standing on stretch all the way across to Northern Ireland, where there's also the Giant's Causeway. But the causeway was ripped up when one giant came across and saw the other giant sleeping, and he thought it was a baby, and he ran back. So that is the story of this place. What you've got is these great gabbro rings coming around, and where we actually are right now, it doesn't show the roads too well.
Oh, there's a midge.
Anyway, where I'm going to take you to is that exact centre point there, that in the cross section is right there. Now, why it doesn't continue to depth, I don't know, but that's the centre of 3. So that's where we're going to head, and we'll be right in the centre. And it's the best place to get a sense that you're right in the heart of this volcano, and it's all ring is around you. That's the plan. And the actual rock outcropping there is marked as QM, and QM is where's QM bloody thing? Where is it? These are Q's. And then you put 2 holes in the slate and you literally bang it in with nails. But this is an example of the pyrite. You know, I was saying how got the poor quality, the rusting. So here's pyrite, and here is iron staining from the pyrite. Whereas this piece here is good,
Good and clean.
Good and clean. But these are very thick. You know, the Welsh slates managed to break thinner and are probably, arguably, higher quality. But this is the slates from here. And then if we come here, this is the main quarry face, and you can see how at the top there's a lighter colour. That's actually the dike that I was talking about. Cutting the slates. Bands here might, I guess, be representing the original sedimentary layering, but then it's the cleavage. The cleavage is the metamorphic feature, and that's what you break the slates on. Oh. And why you get a cleavage, I guess it's the minerals start to rearrange themselves. Be careful, there's got rhyolites. Why have you got ignimbrites? Well, this was a volcano that was very, very eruptive. It was a sticky volcano, a dangerous volcano. It had a big caldera forming eruption that made these pyroclastic flows, and this volcano is Devonian in age. So all associated with the whole story we've been talking about of Avalonia crashing into Laurentia, all the terrains being slid into position. This is at the end of that period. You know, it's the end of the Caledonian orogeny, it's the Devonian. So its volcanism is associated with this. Perhaps actually by the Devonian there's actually some extension going on. So things are crushed up, things are relaxed, there's a bit of extension, and this can allow volcanoes to come up through. So it's probably that type of regime, but it would have been a a great big volcano. So on this trip we've got Carboniferous volcanoes in Edinburgh, which we'll see later on today, Devonian volcanoes here, these are the older ones, but then the Paleogene volcanoes we've been seeing the last few days, which are much younger. Those of you going to Shetland, you're also going to see a Devonian volcano when we get to Shetland. So anyway, I will take a few pictures and we'll get back on the bus, because we've got the Three Sisters. In the handout I flipped them the other way around to orientate it, but these are the Three Sisters. So this one is that one, the middle one, and the far one is that one. And you can see it's sills, various layers of rhyolite. Could I actually maybe take a picture? Some of you standing around this holding it? 'Cause here we are in the beautiful Glencoe in the Highlands of Scotland, and behind us you have the peaks of the Three Sisters, and the rock layers in these peaks were made by a supervolcano in the Devonian period. The bottom layers are sills of andesite, then you have rhyolite layers, and then you have ignimbrite layers, which is where ashes come out, or big pyroclastic flows have flowed out from the caldera forming eruption that would have made the volcano. But these rocks that were formed in this volcano are actually 400 million years old. So what the mountains you're seeing now, they aren't actually like the volcano. They are rocks that were made by the volcano, but it's actually all glacial ice from the last ice age that's carved out the shapes. And in fact, these valleys here are actually hanging valleys from this main U-shaped valley that we're standing in today. Racing out. So that's the reconstruction of the caldera. Whether it's right or not, that's another matter. It probably is right, but essentially what you're looking at is a landscape carved by ice, but the rocks that the ice has carved out of were made in this supervolcano caldera setting, and it's been mapped and shown that there's actually a feed event feeding right up there, and that's why this mountain is harder than the surrounding areas that's been left by the erosion.
So the entire thing is the feeder vent.
Well, yeah.
Is
No, not
what's
exactly.
left.
If you go back to the picture of the mountain, it's of course the mountain. You can
This
see
is-
that this is
Okay.
the mountain. So there's one side, and this is flipped. So it'd be over on this side. There's part of it that's like these sills here that are coming out on the edges, but it's hard to see that. But that's what
Is
you have
that
to
right?
visualize.
Yeah,
Okay.
that's how you've got to visualize. And
Okay.
you know, it's great how the hell they figured it out.
Some bold geologists climbed up there and did it.
Yeah,
They took samples, looked at it, and said, "Holy cow, that's."
geological map. You've actually got the main feeder pipe, the summit of the volcano here, and you've got Salisbury Crags. There's a sill. This is the sill, and there's actually two other sills as well, and this is one of them here. This grassy bank. It doesn't outcrop, but this is actually one of those sills just cutting across here. So what we're going to do is we're going to walk up to where the green fencing is up there, and see Hutton's section, touch the sill, and then we'll come to the right of there, and we'll see some of these vent agglomerates and the material that's come from the main plug. But this is the main feeder pipe of the volcano that used to be here, and it's quite incredible really, because here you really are seeing the shape of the volcano. Apart from, you imagine that would have gone up higher, and then there would have been like a sort of, say, an ash cone all around it, and that's been eroded away. But all of that would have been totally covered by many, layers and layers of more recent rock that's also been eroded away, because this is back in the Mississippian or Carboniferous that this was erupting. Yeah, we call it Carboniferous, you call it Mississippian and Pennsylvanian, and this is lower Carboniferous, which is Mississippian. So anyway, I'm going to lead you up to that green fence, and we're going to sort of walk along the side of the green fence, sort of peer through a gap, and then we're going to touch the sill there, and then we're going to come up to the rocks to the right of it, above where that red and white material is on the road. Okay. Crag, so crossing the sill, and we've got the main Arthur Seat volcano there, and you can see the path that climbs all the way up to the top. We're not planning to do that, but
No, we're not.
if you want to go up in your own free time for city views, obviously lots of people do that, but what you've got outcropping at the top is you've got a vent of dolerite, and actually where the people at the very top is dolerite, but this whole face here, all of it is what's mapped as vent agglomerate. So it's bombs and lapilli and pieces have all been chucked out of the vent. And there's really nice exposures of it just down here though, without having to climb up. So we're going to go and look at those exposures, and then our path is going to, yeah, we're going to go look at those exposures, and eventually we get back to the road there, and you'll get a good view of Edinburgh Castle and its volcano. So, but this is crossing the sill. So,
James, just one moment of orientation. Can you point precisely on the cross section?
on the cross section, we're on this sill here. I'm standing on the sill.
Looking at the
Salisbury Cracks.
Good, thank you.
And the volcanic plug
Is right there.
the very summit of that, where people are
Gotcha.
standing on the top. That's the feeder pipe of the volcano. It literally is. So,
Very good.
There you go.
There he is. Hey.
Thank you, James.
You get a piece of rhyolite when you get 10 punches.
All right.